Hello everyone. Today I want to say a few words about symplectic geometry of Anosov flows in dimension 3 and bicontact topology. Anosov dynamics and on the other hand contact and symplectic topology, they're both theories which have subtle relations to the topology of the underlying manifold, and today I want to explore some relations between the two. In order to put things in context, I should mention that Anosov flows were introduced in early 60s by Dmitry Anosov. Primarily methods from dynamical systems and especially ergodic theory, and later on foliation theory were used to show strong rigidity and global properties of such flows, in particular in dimension 3. And my goal is to give a contact and symplectic geometric characterization of such flows in dimension 3 and use that characterization to set up a framework of using geometric and topological tools in Anosov dynamics. So let me overview a few basic definitions from Anosov dynamics. During this short talk, I'm going to assume that M is a closed-oriented and connected three-manifold, X is a non-vanishing vector field on M, and phi is the flow generated by X. So we call a C1 flow phi Anosov if there exists a splitting of the tangent space into three line bundles, ES, EU, U, and the direction of the flow, such that the splitting is, first of all, continuous and invariant under the flow. And when you apply the flow to the vectors in the EU direction, the length of those flows, those vectors would exponentially expand. And also, if you apply the flow to vectors in the ES direction, the length of such vectors would exponentially decrease. In this definition, A and C are positive numbers, and we call the EUU the strong unstable direction and ESS the strong stable direction. So here you have a picture of how the dynamics work on the tangent space. A few examples are suspension of Anosov diffeomorphisms of torus, the geodesic flows up on the unit tangent space of hyperbolic surfaces, and also according to Foulon and Hasselblad, we have many examples on hyperbolic manifolds as well. So I mentioned that these flows, they have admit interesting global properties. A few of them are, first of all, that we can see that the fundamental group of such flows, a manifold supporting such flows has exponential growth, meaning that it's very large. That also implies that there are no Anosov flows on the sphere or torus or Niels manifold. Another interesting property is that there is no contractible periodic orbit for such flows. And there are many generalizations of Anosov flows, but there is one of them that is in particular related to contact geometry. So we call the flow a projectively Anosov if its induced flow on the normal bundle of the direction of the flow admits a dominated splitting. That means that there exists again continuous and invariant splitting of the normal bundle ES and E into two line bundles ES and EU, and the relative length of vectors in the EU direction over vectors in the ES direction would increase exponentially. And unlike Anosov flows, we can see that projectively Anosov flows are abundant. In particular, we have like infinitely many distinct projectively Anosov flows on the sphere that it doesn't admit any Anosov flow. And it turns out that a vector field is the generator of a projectively Anosov flow if and only if it's in the intersection of a pair of transverse positive and negative contact structures. So let me say a few words about some basics of contact and symplectic geometry. So we call a one form alpha a positive contact form on M if alpha wedge d alpha is a positive volume form on M, and we call it a negative contact form if that alpha wedge d alpha is negative. And we call the kernel of such one form, which is a plane field, a positive or negative contact structure. So here you see an example. Alpha standard defined on R3 is equal to dz minus y dx. You can easily confirm this is a contact form, and in fact, you see in the picture, you see an image of how the kernel of such one form looks like. It turns out that contact structures, they don't contain any local information thanks to Darboux and Gray's theorem. So that means that their subtlety is more related to global and topological properties of the manifold. There's an important dichotomy related to these global properties. So we call a contact manifold over twisted if it contains an embedded disk that is tangent to the plane fields, to the contact structure along the boundary. Otherwise, we call it tight. So it's not clear from the definition why it's an important dichotomy, but it is important thanks to the theorem of Eliashberg, which basically tells you that the study of over-twisted contact structures can be reduced to algebraic topology, while tight contact structures, they're harder to understand, and then when they exist, they have more subtle relation to topology. One way to establish this tightness property is to relate the contact manifold to some four-dimensional symplectic geometry. That's thanks to theorems by Gromov and Eliashberg, saying that if a contact manifold is symplectically fillable, then it is tight. So a few words about symplectic geometry. So let Y be an oriented form manifold. The two-form omega is called a symplectic structure if it is closed, and also omega wedge omega is positive. So again, you have this standard example on R4, and all symplectic structures, again, they locally look the same. So you have some standard model, and we call a contact manifold exactly symplectically fillable if there exists some symplectic manifold with boundaries such that the boundary of this four manifold is M as oriented manifolds, and omega, the symplectic structure, is exact for some one form, like is d alpha for some one form alpha, which its restriction to the boundary is a contact form for C. And we call such one form a Liouville form. And it's important that there are more general notions of symplectic feelings, namely weakly and strongly symplectic fillable contact manifolds. I'm not going to mention them here. So these definitions basically they give you a hierarchy of contact manifolds. On one hand, you have a general contact manifold, and on the other hand, you have exactly symplectically fillable contact manifolds. A very important special case is when you have a pair of contact form alpha minus and alpha plus. We call that a Liouville pair if these are like a positive and negative contact forms, and their linear interpolation is a Liouville form on M cross interval. So I'm ready now to tell you about my main result. So my main theorem is that if you have a C2 flow on a 3-manifold M generated by some vector field X, then phi is Anosov if and only if the direction of the flow X is in the intersection of a pair of positive and negative contact structures, such that there exists one forms alpha plus and alpha minus for these contact structures, such that alpha minus alpha plus and minus alpha plus, they're both Liouville pairs. So notice that this is a like full characterization of C2 Anosov flows. So motivated by this theorem, we call such a pair of contact structures a bicontact structure. And in this situation, we say that that bicontact structure supports that projectively Anosov flow. So notice that for the vector field to lie on the intersection of these two contact structures, that was equivalent to the flow being projectively Anosov. Few words about the aftermath of the theorem. So I'm going to talk about three different directions that you can go from the main theorem. One of them is to talk about contact and symplectic topology of Anosov flows. It turns out that now you can look at this Anosovity as a bunch of like contact and symplectic geometric conditions on a projectively Anosov flow. So we can transfer the definitions from symplectic and contact topology to Anosov dynamics and get an equivalent, basically, hierarchy of Anosov flows. On the one hand, we have Anosov flows, and on the loose end, we have projectively Anosov flows, and we can define tightness and symplectic feelings for such flows, and we can ask what does each contact topological layer imply about the dynamics of the underlying manifold. In a work in progress, we can show that universally tight projectively Anosov flows, they don't admit any contractible orbits. We can also ask about the properness of such inclusions, and we can show that there are weakly fillable projectively Anosov flows which are not strongly fillable. We can also ask more dynamical questions about like what happens about like when you like perturb or like deform projectively Anosov flows. We can ask about whether like projectively Anosov flows are C2 structurally stable, or we can ask whether two Anosov flows which are supported by homotopic bicontact structures are orbit equivalent. Along these lines, we showed that at least for a fixed projectively Anosov flow, there is a unique supporting bicontact structure up to bicontact homotopy. And finally, according to the main theorem, periodic orbits of Anosov flows, now they can be realized as Legendrian knots and Lagrangian analy. These are well-studied objects in contact and symplectic topology. Now we can use these geometric metrics methods to investigate questions about such periodic orbits. Thank you very much.